give now a lecture on random number generation in C++, past and present and potential future. I gave this one in ACC conference that was in Bristol. Now I want to present it in YouTube so that people can watch. It is a general topic. So, and there are a lot of improvements happened in the past decade, and recently in the first few years there was a lot of developments. So that we'll be discussing now, and we have delegate Ms. Vinis De Silva, and she'll be participating here as a to help this presentation. And Vinis, could you please introduce yourself?
Hi, my name is Eunice De Silva. I work in investment banking and specifically in risk management, where we use a lot of the techniques in Monte Carlo simulation. And I've been assisting the course with Professor Vitaly Roman to understand how the techniques work.
Thank you, Eunice. Let us see. What is random? It represents an event or entity which cannot be determined but only prescribed probabilistically. That means we can't say this going to happen or that going to happen. Anything between this and that, anything can happen. That is the random. So, for example, we have falling raindrops which hit the ground in random pattern. Distribution of stars within the universe is a random. And baby cries in random, and so on. Okay. So, what are the use of random numbers? They are mainly used in simulations, be it a numerical calculation or a cartoon game. Binding analog data in channel format. Testing a product to test whether it serves all the overall testing. For example, we are giving the all input parameters to see extreme conditions and normal conditions, and for that you will be applying the random numbers because that can go from one extreme to another extreme, and on the average everything it will cover. So it is very useful in testing products, and there are many applications. What is the plan of this presentation? I will talk about historic evolution of random numbers and their applications, the modern development and implementation in C++ and beyond, because C++ is a standard language. So it takes anything after knowing that it was very useful to the public, and it can be a standard one. For example, there are a lot of new developments are happening, but that was not tested. Everything was not tested, and everything was not useful to the public. So that won't be coming into the C++. So once it comes to C++, we can say that is very good standard, and we can also say that is that is going to exist for decades to come. That method, and C++ is an ISO language, programming language. So that guarantees that if we code a program, that code will run after 20 years also, because that is the standard. And beyond means what we are going to study about the beyond means that of GPU programming has come, CUDA and accelerated mass programming. That also will look into that, how it will help the random number generation and simulations. How did random numbers and their application evolve? So let us see. It has evolved in prehistoric time. That ancient tribes, that is million years maybe, at that time they using dice to produce random numbers and playing games. So that was they started gambling at the time itself using random number. And then in the Bronze Age, the gambling became unethical. Even kings involved, they lost the crown to opponents. So then what happened in around 300 BC, the regulation started for gambling because random numbers should not be used too much near very destructive manner. And up to 1650, people are using dice to produce random numbers. But Pascal, who made the mechanical calculator, he devised a physics experiment for proving the conservation of energy. At that time, his wheel, he made a wheel such that it runs for long time and then settles at a random point. So that became a basis for invention of roulette wheel. The roulette wheel had a more advantage than dice because that can produce more numbers, and that was more convenient for gambling. So the gambling houses, instead of dice, they started using roulette wheel. Then in 1930, Enrico Fermi, who is a physicist, he wanted to do sampling of radioactivity, radio decay, because radioactivity is a random. So it can emit alpha or beta, so and then it can change chain of decay. So at the time we want to see what are the possible paths. So you need some random numbers to make an estimate. So you could not use the roulette wheel because that won't produce enough number. So he made one instrument called Fermiac, that is called the Monte Carlo tally, and he generated random numbers from that. That was useful for making his decay chain. Then in 1940, Stan Ulam, who was a good mathematician, he was playing a solitary game when he was recovering from his surgery. So that one can play on his own or on her own. Then he thought, if I would have played for 100 games and take a note of how many I got success, then I can understand what is the average success. So that is called probability. So that became the basis for the Monte Carlo method. Then John Newman, he was a friend of Stan Ulam. He discussed with him and learned how to make the probability using the simulation. Then he applied that idea in various problems. He wanted to make a proper simulation. So instead of the Enrico Fermi's mechanical random number producer, he wanted to use computer. So at that time, the first electronic general purpose computer was ENIAC. You can see people working inside the computer. So, and he wanted to use that computer to produce simulation. So to produce simulation, you need random numbers. So at the time, they collected random numbers from nuclear radioactivity, voltage fluctuation, solar flare, and a lot of physical activities. From there, they stored it in punch cards, and then put the punch card inside the computer, and it will read and then you can do simulation. But reading from punch cards are very slow. So what he developed, what he did, why don't we use some arithmetic instead of putting a physics number, a physically obtained number? Let us let the computer generate on its own a random number. So he used the 13th century mid-square method, where if you give a number as a seed, then it makes a square and takes the middle part of that number, and that middle part becomes a new number, new random number. Then square it to get middle part of the new square number as a new random. So this method is called mid-square method. However, this method is so inferior to the random numbers obtained from physical events. So people criticized him. However, he said, I need to do simulation. If I need to do simulation, it has to be fast. Then only I can do my calculations. And if I go on depending upon punch card, then I can't work with that, because my calculations are huge that needs fast computation. So I need to produce random numbers from computer. So he said, anyone who considers arithmetical method of producing random digit is, of course, a state of sin. Then he used the Monte Carlo method and successfully helped in designing and testing the first thermonuclear bomb. And very interestingly, his simulations are helped him to try about weather forecasting. So he is the first person who did the weather forecasting and estimated climate change. So this is the first paper in weather forecasting. He used his simulation and then explained about how the weather will change in due course of time or in a seasonal time. Everything he explained, and he also predicted the climate change of global warming in 50 years time. So he became a leader in weather forecasting, and his simulation idea helped in writing the first game theory. And interestingly, he made he simulated one method called replicators. That is the base for discovery of DNA. So, and then the simulations are in some time goes wrong. Sorry, in some time it went wrong. Then that jammed the computer, that big computer. So that from that people got the idea of how to make virus. So he's a father of virus or computer virus also. So all these things he did with the use of random numbers, and that was very successful. From that, people started using it in every field. So if you do any financial calculations, if you say I derived it by mathematical formula, then people will have some doubt. But if you say I derived it by simulation, then people give more weightage, more trust to that, because that is proved that it is helpful, it's reliable. Then in 1957, we got Fortran language, that is formula transition system, that used it better method than the mid-square method. So they gone for the multiplicative congruential generator. What is congruential? Congruential means piecewise. So it will generate random numbers in piecewise. How it generates? It's just like that. Y equal to mx. Okay. there is no C here, just mx, y equal to mx. M is the slope, y is the new random number, x is the previous random number. Here you see the regression relation, you have the x suffix n, that is the new number, new, and a suffix a is a constant term, okay, that is a constant, or you can say slope, multiplicative factor, and x suffix n minus 1 is the previous one, previous random, okay. And what is mode? Mode of m is you divide by m and find out the remainder, that is called modulus, mod m. In C++ you can write like this, x of I equal to a star x of I minus 1, then percentage sign m, okay, semicolon. Make sure if I minus 1 is greater than or equal to 0, because if you are doing it, if I equal to 0, then and then you have to see this one also, range also, another range is I supposed to be greater than the size of the array. If you want to check it, become a range here. Okay, so you have to make sure that the I is within, should be greater than or I minus 1 should be greater than or equal to 0, and I should be, sorry, it should be less than size, and ampersand, double ampersand you can put. Okay, then check this condition. If it is there, then evaluate the new random number from the old random number by this constant, multiplying by this constant and getting the modulus. What is modulus of 25, 4? Is it? Tell me, please.
Oh, you're asking me.
Yes.
It's 125.
What is actually, if it is an integer division, okay? So 25 by 4 is,
125.
so 24 comes, okay? So remainder is 1. So its remainder is 1. Okay? Can the remainder become more than 4? No, because it will be less than 4. So the cycle is like this: 1, 2, 3. Okay. So this is the limiting factor m. So you have the new random number is a previous random number times a constant, that is slope, and m, modulus of m. Then they wrote it in fortran. It is random equal to mod a star c comma m, and then they got this. And then after some years, they put it instead of multiplicative congruential generator, they put it linear congruential generator. It is like y equal to mx plus c, where m is the slope, c is the constant term, or the which it is the c. Here c, this is the m. Okay, here dx, so dy dx. So dy by dx is m, and this one c is the where it cuts the y-axis. So that is the, this is the random you are doing. But if it goes beyond m, then you will be coming back. Okay, that is the, like a spinning around up to the m. Maximum you can go up to m. Okay, so this is the another the improved method of compared to multiplicative. However, this is not a very sensitive one. You see, so some now also people use b equal to 0. So both are okay. Then in 1972, C language was established. There they used the linear congruential method. So here you see the A, B, and next equal to next star A plus B, and then you are returning by next by this number, and this is the size of the short integer, and then modulus of half value of short integer, because it's a signed integer. If it's a signed integer, then we can go only off of this size. So that's why it's 32,000. So that is the bottleneck. So you can't expect a random number beyond 32,000. Correct? Okay, that is limit of the C language random number. And then here is srand to set the seed. Okay. And in program, you can put srand time null. Null time means present time. So that is given as the random seed. It sets a random seed, and then you are beginning the random, and you are dividing by random max. So what is the maximum value of random that you are dividing it? Then that give range between 0 and 1. So you got the random numbers. Then in 1983, C++ was established. It is nothing but C program with classes of Simula. So it uses the object-oriented orientation as well as normal, and it has the both advantage. It has the object-oriented programming as well as proximity to hardware. And this C++, when it was established in 1983, it had just borrowed all the mathematical library CMath of the C programming. So you have to include CMath. Then you can have all these random numbers and other max facilities from C library. And here you can see random shuffle. That is an algorithm, STL algorithm, that uses the random number. So for example, your initial data is 1 to 10. It shuffles the random. Shuffle data is this one. So this is the function. Random shuffle, data begin, data end. So beginning of vector and ending of vector. So then it shuffles the data. So this is these are the 4 functions which were in the C++ initially. However, people didn't feel very comfortable with this random number facility because that runs up to 32,000 period, and then the quality of random was not satisfactory. So some people gone back to nuclear age, that is the taking the data, random data from nuclear radioactivity, and then generating a physically obtained data, and then store it in the computer and do simulations using that random numbers. However, that is not applicable to every field. If you are doing fast calculations, then you need to still generate from computers. So because if you store it and reading it this will be a time taking process. So there were a lot of development happened during the last 20 years for the methods in random generation. So you can watch this video on YouTube. It's a good method, however, it is a time taking process. You will get good random numbers. So and then you can see in 2006 the effort has started. People from Fermi Lab, this Fermi Lab people started putting the effort in implementing the new random number generators for the C++. So they started in 2006 and it was established. They put separated their file called the random. Then in about year 2009, this new C++ facility started coming, and it was established in with C++ 11 standard in 2011. So it has dedicated sublibrary called random, and it has two major parts: distribution and engine. If you distribution as a function of engine, you will get random. So if you want to get a random number, call the distribution with, and then within the parentheses supply the engine. Then you will get the random number. So it has two major parts: engines and distributions. In engines, we have linear congruential, subtract with carry, machinery twister, and engine adapters that will modify the engine's output. Then you have true random generator called random device. These are the classes added. Similarly, in distribution, you have the uniform distributions, normal distribution, Bernoulli, weight-based distribution, piecewise, canonical numbers. So we'll first go through the engines, then we'll do some distributions. So what is linear congruential engine? That we already saw in the early period itself. People give up the mid-square method. They started coming to the linear congruential engine method. That is the linear, like just like a linear y equal to mx plus 3, and then they will make a percentage of, make a modulus of m. So we have two engines of this method. One is called min std rand 0, which has the constant is, and min std rand is a different constant. Our m is there, but have you noticed the value of m? Earlier it was unsigned short, half of the signed short value. Now it become a long integer. Okay, so you can have this is the limitation. You can have up to 2 billion numbers, random numbers. Okay, so in this case, what is your limiting factor? Of course, this a is value is limiting factor. However, still, now if you take this one, this curve, so the limiting factor is m. Earlier, m was short. Okay, it is 34,000. Now it is 2 billion. Okay, 10 power 9. Okay, earlier this was 34 10 power 3. So you had that much in the C rand. But now the linear congruential, that is with the engine, you can have C++ 11 here. Okay, your large area a large period of numbers. However, the value of A matters because that can also make a periodicity shorter. And the main bottleneck is this one, M. Then subtract with carry engine. In 1991, that method was established, and it has been put in C++11. What is this method is, it is similar to linear convolutional algorithm. In linear convolutional algorithm, you can see x suffix n, that is present random number, is obtained from previous random number. So it is a function of previous random number. However, lagged Fabbriconi algorithm is the basis of subtract with carry engine. So this lagged Fabbriconi is a function of 2 or more previous random numbers. Okay. So it is like this. You have one previous random number, another previous random number. Okay, and then you have a this CYN. CYN is nothing but it is a 0 or 1. Okay. If it is this number, this entire thing comes less than 0, then make it 1. Or if it is more than 0, then make it 0. And then there is a modulus of M. Okay. So here it depends upon 2 or more previous random numbers. So you can have more sophistication in getting the random number. However, it leads more error also because you are taking error from this random number and error from this number. So you are adding up more errors also. So it has more advantage as well as more error. So in this one we have two engines. One is RANDLX 24 base and this one is 48 base, okay, with different parameters. And then there is a wonderful engine and Nestle Twister, and it was established in 1997. It is based on an algorithm called Twister Generalized Feedback Shift Register, and its period length is 2 power this much, which is greater than 10 power 6000. Okay, so now what is the case? We are doing like this. If this is the curve, this earlier M we said, see, and this is the linear congruential. Okay, and present C++ engine, C++11, C++11. This also C++11 is but that goes almost infinity. Okay, it is 2 billion, 2 into 10 power 9. It is 34 into 10 power 3. It is more than 10 power 6000. So it is a very large number, 10 power 6000. So then that is a period length of this twister. And what happened? What is the advantage? It has gone through many random number algorithms and then chosen good points and then made this algorithm in such a way that it is it's wonderful. People use it as a default engine in many code, many compilers. We have two engines, MT with 32-bit and 64-bit. Then we have another one, random divide. That is a engine which generates random number if hardware supports. Because some hardwares can support this can generate and store random numbers in a space called entropy. So how it generates? It generates from sub voltage in motherboard, sub voltage noise in motherboard, and then number of thread used, what is the date, time. From everywhere, it generates random. From all this data, it generates random and store it in the entropy. However, that won't be sufficient for our normal simulation. The numbers will be limited numbers. So you can use this as a seed. For example, you can use here uh, compose this random device and RD. Then you can make the call the default engine E1. Like default engine is basically mismatch twister. Then compose this one. Put the RD as a seed. Okay, while declaring E1, you're putting it as a seed. Then this number will be a seed for this E1. Okay, so this is a seed. Okay, and there was a problem with C language because if people do simulation with C language and in a one machine and they do it in the other machine, the results are not matching because the random number generator was not given a condition for what are the constants should be used, what are the parameters should be used. So they said the method, but didn't describe the value of parameters. So different compilers use different parameters, and the simulation made by one compiler is not the same as the made by another compiler. So that was inconsistent. So in C++11, what was they put? They put a required behavior. So if you in the required behavior, what they mentioned, look at here. If that 10,000 consecutive in the random number of this they put for each engine, for this engine, it should be this value. If you won't get this value at the 10,000 count, then you haven't implemented properly. So what user can do, they can make their own method, a class, set empty is a member function. I wrote it in my class, and then I am checking it here. So I run this engine for 999,000 times. Okay, sorry, up to 0 to this much. That means 10,000 times I am running, and 10,001 I am checking whether taking this as a number 10,001 and checking whether that number matches with the required number. If it is there, then it is implemented properly. I can believe I can use it. If it is not there, then I can reject the engine. I have to complain to the people who made this software, who made the compiler. So now it's a consistent one. So we can all compilers are they're mandatory to check these numbers. Therefore, we can easily believe on all established compilers for C++11. Now let us see how the distributions are made. We discuss about the engines. Now we'll see about the distribution. We can do using bind function. Bind function is like a lambda function. You can use either lambda function or bind function or function object. So in bind function, if you see what is the bind function, it has two parameters. It is binding two parameters. One parameter is uniform real distribution of type double. It is a start point is 0.0 and stop is 1.0, and then you are binding it with a default random engine, usually empty. Twister. Then the output what you will get from bind is a function called dist. So and then whenever I want random number, I can call the function. It will produce the random number of uniform distribution from 0 to 1 using the mission register. Okay. Now we can use the same thing with a class. Okay. So class uniform distribution, and this here you can see the function object operator. Okay. So whenever you call this uniform dist, compose this class and then call it. For example, if you in your program, teacher main compose this one uniform distribution UD. Then how can you generate random number? That is nothing but if, for example, auto random equal to 0.0. Now you can put random equal to UD empty bracket, because empty braces if you put, that will directly come over here and it will call the uniform engine. Okay. What is uniform? That is this one. And here you are initializing with uniform of 0, 1. That is nothing but your uniform real distribution. Okay. Uniform. And the default engine you consider as the engine. Then you are having the this is the function of operator. This is the default constructor. It puts default value of 0 and 1 for the starting and stop point, and then we have the constructor here. Okay, that gives the low and high value. So if you construct with different low and high, you can make different start point and stop point. You can change it using this constructor with arguments. And then you have the discard. The discard is useful in concurrency. That we'll be discussing it later. Similarly, you can do for normal distribution. Here, instead of uniform distribution, we called normal distribution. Other things are okay. Here, instead of start value and stop value, or high value, low value and high value, we have mean and standard deviation. Because a normal distribution, it needs mean and standard deviation. Because this doesn't have any start or stop. Because start is minus infinity, stop is plus infinity. So if you if you run that code, we'll get an output that will be plotted like this. So it comes from minus infinity. At 0, it goes to the peak, and it goes up to plus infinity. You can see the counts are very low. Actually, it's not the real counts. It is normalized count. What the real count? I just counted the total sum and divided by that each channel by that number. Then I got this decimal points. The count cannot be decimal one, and this is a normalized one. So the total area under the curve is 1. Why we normalized? That is very useful for a lot of simulations. I want to give you an idea about how the distributions are made, because random number generates in uniform basis, and we can make different distributions. This normal distribution or exponential, lot of things you can do. You can change from one distribution to other distribution. How can you do? Is it if you want to make this distribution into flat area, that uniform distribution, what you have to do? Get your hammer and press it on the bell. Correct? No, that we cannot do numbers. So what we'll do? We'll do a transformation. So here the psi of x and here what is look at this one. Is in the above graph, it's called cumulative normal distribution. We're summing up the pi of x at each x point. So in the bottom curve, you can see -4 point -4 x. If you sum up all the count from -infinity to -4, you will almost get 0 only, right? So put a point in the above graph, the top graph. Put a cross at this point. Okay. Sorry, I should put it in this point. Okay. And then if you look at the, if you sum up all the counts from -infinity up to 0, how much count you will get at 0? The total count is 1 because total area under the curve is 1 because it's normalized. So up to, if you sum from -infinity to 0, how much you will get? 0.5 or 1? Is it 1 or 0.5?
Oh.
This one is -infinity to 0. We are summing up all the area under the curve. Okay. So 1 is the full area under the curve. Now we are doing only half of the curve. Okay. In the half of the curve, if you do sum up all the counts here. Okay. Sorry, this is not a perfect curve, perfect line, but it goes through the axis, 0 axis. Okay. 0 y axis. So if you sum up all the things, everything you sum up, okay, then how much count you will get? For total sum up you will get 1, but half of the sum up you get 0.5, correct. So you will get 0.5, and for if it is a +4, how much you will get? To sum up to +4 from -infinity to +4, then how much you will get?
After that.
Hmm?
After that, so for the.
Yes, it will be 1 or half or 0 at 4. If you sum up the count here, if you put summing up all the pi of x, okay, up to 4, x is 4. Okay, summing up all the counts under the curve up to 4. So add this curve, all the curves add up to 4. What will, if you sum up all the count, what will be the value? 4. It is option is 0.5 or 1.
If you sum up everything, it would be 1.
1, very good. So you will get here 1 at 4. Okay. So then you will see how the curve will be. Okay. This is the called cumulative normal distribution that goes like this. Okay. And you see, interestingly, this range is earlier, it was the below graph, it is -infinity to plus, sorry, yes, -infinity to +infinity. Okay. But here you see range 1 to 0. So you modified the distribution from -infinity to +infinity to 0 to 1, right? So this is similar to uniform distribution, not exact distribution. So that needs a mathematical method to convert one distribution to other distribution. So you can see that conversion. It's a method of converting a uniform distribution to normal distribution. Can you see the large numbers here? Right. So that's why some people do editing the this method, these codes. However, that is not safe because we can't understand clearly about these numbers, how they got. and what are the each thing is doing, we can't understand, and God is only given the task to number theoretician. If they established a code, tested it, that we have to use it instead of modifying or writing our own code. That's why people say, please avoid coding random number generators or distributions. Make use of your compiler and numerical code. Okay, code in the numerical recipes. Then at the time, I was started writing a C++ group for making a simplified learning process for C language, C++ language. I used the at that time the C++ 11 library was new, so I made with a lot of features in C++ 11. Then I tried to do a simulation using this random library, using random from C++ 11. So here the pi is the normal distribution of the obtained from the random library. This is the random, and then we got the simulation working, and we could get the expected results. However, when I did the performance analysis, sorry, not performance analysis now. This is just a non-concurrent simple serial program. Then I tried to use the concurrency. That is a concurrency C++ 11 produce concurrent libraries called red, then future, then mutex, then atomic, and so on. So here these are the very useful, and atomic is bit of our library developers, very important. However, it's not a very user friendly. These are fine for doing the concurrency. So here I used the future and then made the program into concurrent one, and then I tried to do the performance analysis. So the performance analysis I could see this is called performance. In this one, you see pi. What is pi? Pi is the function of normal distribution. Normal distribution is a function of Mr. Twister. Okay. So this one, without pi, the code picked up the speed. For example, I used different codes: 1, 2, single core, double core, triple core, 4, 5, 6, and I'm seeing the speed up how it increased compared to serial. So single core is like a serial program. It was 1, fantastic, no problem. When it was 2 core, it is just less than 2, and when it is 3, it's just less than 3. Then when it is 4, it was bit about 3.5. When it is 5, it is about 4.2. So this is expected with Admel's law says if you have hardware here, hardware, this is software. Okay, the software grows to speed up performance of performance. Okay, performance is of this one. Software is slower. There is the both are expression. You can see here. Hardware goes like this. Okay. The software goes out like this. Okay, software won't, it's not growing. That performance of software is not growing as like hardware, because as you, even though your hardware goes, the serial part of the code will pull you down, will not help you to push up too much. So you can see up to 3 core it's fine, but when it's 4 it is coming down, when it's 5 it's coming more down. It's not going to up to, sorry, it is growing, but it's not growing as good as the hardware grows. So at 6 you are getting only 5. At core 6 you are getting the value of 5. Okay, that is fine. But when I apply the normal distribution, then I got very low value. The slope has fall down. Can you see? So please, can you see, agree? The slope of the with normal distribution, the speed up has reduced. For the 6 core, I can go up to only 2.5, right? So this is a problem. Then I used the Admel's law. This is the Admel's law's method. So you can see where S is the speed up, N is the number of thread, okay, P is the parallel part in a code. That shows without pi you have almost 100%. The code is parallel, 100% parallel. With pi, your code is 60 to 70% parallel, right? So that's not a very good idea, good thing. So it shows about 30% of the normal distribution of the random library. This goes in parallel. This goes in serial, not in parallel. Okay. Sorry. 30% of random is serial. They are not parallel. Okay. So this is a issue to be understandable. And I haven't had a good idea about concurrency, and so I approached the C++ library. After doing all the engines, some engines you see the deadlock has happened. Deadlock means the data is went so bad that nothing is moving. Okay, in the concurrent mode. So then I took this issue to standard committee. The standards committee was there in Bristol last year. So I went them and even discussed with people. I'm thankful to all the people. And what are the discussion they made is, if you look at the standard library, it has a template. Mr. Tester engine is a template. That template has a class. Mr. Tester is a template, and it has a public, and you have the all the member functions, and there is a important member function that is called operator. Okay, function object. This operator, this operator is constant. If it is constant, the constant method, then it would save for concurrency. If you put constant here in the declaring or using the defining the any function of any member function, then that is called that constant member function or constant method. Okay, if it is constant method, then that is safe in calling concurrency, but it was not a constant, so it's not safe for not for concurrency. The purpose why it is not constant is the standard library wanted, if you call one engine, it has to serve different threads. That is the idea. So they don't want to put constant, and the constant also is not um, correct way also, because you are going to change the numbers all the time. Random numbers always getting generated. So the idea of this, since it's not constant, so it is not safe for concurrency. So what is the idea problem would happen is, if you have a thread, if you have a random number generator, and you have 4 threads. Okay, let us take thread 1, thread 2, thread 3, thread 4. And if all threads are reading from the same engine, that is fine. But each time when they read, it writes out the next number. Okay, so it's writing or editing. So whenever each thread is asking, it produces the new number. Okay, so we know in concurrency, writing or editing is not safe, because if both ask for a number, if it is data arrays, the random number generator can't separately give one number to one thread, another number to another thread. It may give same number to both threads. So that is called a data arrays problem. So if for that data arrays problem, if you use lock guard, that is fine. That will solve the data arrays. But it solves data arrays, but much slower than non-concurrent. Okay. So log guard is not useful, because you don't need to run any concurrent program. You just run serial program. That is faster instead of using log guard. Because log guard takes a lot of time. It is regulating the queue. However, it takes a lot of time to regulate the queue, because the threads are so naughty. Like this police log guard can't do it in a very quick manner. Okay, that's why we can't use lock guard. We can't use such for the concurrency. So then, what is the another idea? You declare the random generator as a thread local. If you while composing the random generator, if you declare it as a thread local, then each thread can have an independent copy of the random engine. Okay. Okay. Each engine will have its own access to the random number generator. They won't interfere. But the problem is, it will provide same set of random numbers in all threads. Correct? So it is a multiplication of same data. Therefore, that cannot add to statistics. Right? If you are giving same, if you are running the same number many times, it won't be a statistics. For example, if you are collecting data from 10 people, and you're supposed to collect from 100 people, okay, but you are collected data from 10 people and multiplying the same data for 10 times. Can you make it 100 people statistic? No. So you have to go to 100 people and collect the data. Similarly, you have to get each thread should get different set of random numbers. They should not get same random numbers. So the solution was construct independent engines for each thread and set different range. For example, if you are using 4 threads, T1, T2, T3, T4 have different engine. T1 E2, E3, E4. Okay. So different engine and as well as distribution also. Distribution. Each have separate one. Sorry. So then you are collecting each thing. What is the drawback here? Instead of having one engine, you are having 4 engines. Okay. Now instead of one engine, you got to 4 engines. So that makes a performance overhead. Right? It's a extra over. It's an overload. It's called overhead. So the computer need to handle 3 extra engines. If you have 8 threads, you have to add 7 more engines. So number of thread increases, number of engine increases. So that makes a bit of time delay. And another thing is, if this number goes from, for example, you are each thread you are supplying 10,000 random numbers, then this will go from 0 to 10,000 random numbers. Okay, and set this one to start from D2 go from 10,001 to 20,000. Okay, and T3 will read from 20,001 to 30,000. Okay, this one T4 will read from 30,001 to 40,000. Okay, so what is the, you see, you can't read as such. You have to discard 10,000 each. Here what you do, call the discard member function. Discard 10,000. Here the second thread, how many numbers you have to discard? Please can you tell me? In the first engine you don't need to discard because we are doing from 0 to 10,000. The second engine you have to discard 10,000. Okay. In third engine, how much you have to discard?
Another 10.
Another 10. So it becomes 20,000. Okay. In fourth engine,
Another 10.
yes, 30,000. So if you have 10 cores, then it become 90,000 discard. Okay. So you are discarding lot of numbers. This discard is slow. Okay. Discard is not fast. Let us check. Let us do the experiment. So here, how do you discard? We have the function object that in the class we have the discard. Okay, discard means discard the engine. Discard. Sometimes we may need to use the discard distribution. You need to discard distribution. Our discard engine is good enough. So if we do this one, we'll try to see everything and we'll get the idea. So then we got the plot like this. We took 4 threads, okay, and then we used to separate engine. So T1 is for E1, T2 for E2, T3 for E3. T is the thread and E is the engine. Okay, they each have a separate independent engine, and then but there is no discard is supplied. At the time you see the speed up here. Okay, speed up. The speed up for 4 thread, it is 3. Okay. Okay. This is the y-axis, x-axis speed up. Y-axis is the different scenarios. So when you are having independent engines for each thread, and you are finding the speed up, it is 3. We expect for 4 thread, it should be near to 4 or at least 3.5, but we are getting 3 because each thread has one engine on distribution, so that makes overhead. So we are getting 3 for 4 threads. However, since it is no discard, all are reading same number. So that is called, it multiplies the data, not the increasing statistics. So we can't use that. We need to discard so that every thread will get different set of random numbers. Correct? So this is the correct. However, you see what is the speed up? It is 2. Right? So the speed up has decreased to 2. Why? The discard takes more time. Okay, complexity is high. Okay, complexity means time taken by the object is high. Algorithm is high. This is because of discard of each the out of 4 thread. The first thread can read as such, whereas here you have to apply the discard in T2, T3, T4. All needs discard some set of numbers. So that is the complexity is high. That takes extra time. So your speed up is just 2. Okay, but when you discard the distribution itself, then what happens? What is the discarding distribution? You are calling the full data in thing. Now you are getting the engine and getting the making normal distribution and then discarding it, not using it. Okay, not using is discard. So you are discarding the distribution. That takes longer time because you are engine need to you are calling engine as well as normal. There is just engine discard is a bit faster, but when discarding the normal distribution itself takes long time. So you see, it is 9.985, which is slower than 1, whereas 1 is serial without any concurrency. Okay, so this is discarding distribution. You can't use it because for that you use normal non-concurrent serial code. Okay, so when you are using concurrency at the time, you want to see improvement. Okay, however, it should be safe. You should not read wrong data. Okay, so this is multiplies the data, not erasing, increasing the statistics. No discard, and discard distribution is worse. You can't think about it. So discard in engine is the safe. Even though we are sad that we can't go up to 4, but we can't even go to 3, but we are going only 2. For 4 threads, we can go up to 2. Is a safe. Okay, we have to satisfy with that. The discard is a the function which makes sure every thread gets different set of random number. That is very useful as it is more time taking algorithm. This is complexity is high. We need to discuss with the number theoreticians to see whether they can help. Okay, complexity of discard, performance time should be reduced. So the number theoretician can help. Okay, to reduce, to find out how can we discard instantly without going through each loop. That will be very useful. And quasi-random numbers. We were seeing that with pseudo-random numbers we could achieve for 4 threads speed up of 2. Okay, double for instead of 4 times we are going for 2 times. That is the limitation. In now that was the whatever the random numbers we generated so far is pseudo-random numbers. So that is the limitation for them. And there is another one method is called quasi-random numbers. That is very good for getting the result quickly. It's going to save the time. So let us look into that. So this topic is quasi-random numbers. So we'll see what are they, then we'll see how they are different from pseudo-random numbers, and then we'll see how they can help. This quasi-random numbers is a systematic building up of gaps. So if it is a sphere or a circle, I'll put a point in the middle. Then I will put it on next edge, the next edge, the next edge, the next edge. If you give me one more point to put, I'll see one safe place to put. So I have systematically put points over the circle. This is called quasi-random numbers. They are not random at all. They are systematic. Okay. That's why they are called low-discrepancy sequence. We'll see about it. Here you see quasi-random numbers, low-discrepancy sequence, and there are three categories of them. Three types of methods. One is altern, there is Niederer zinc. So it's n zinc, and next is Sobel. So if you compare with a pseudo-random number, it would look like this. The pseudo-random numbers are not systematically distributed. What are the methods we saw? The pseudo-random numbers: linear congruential, subtract with carry, vicinity step. Right? And you see the distance between the points, which is uniform, which is less uniform, pseudo or quasi, which is uniform.
The quasi.
Yes, quasi is more uniform. So if it is more uniform, it's more homogeneous. And this discrepancy is a function of inhomogeneity. Okay? Discrepancy is function of inhomogeneity. Okay? This is, let's say, it is more inhomogeneous, and this is less inhomogeneous. Okay? So non-homogeneity is more in pseudo-random numbers. So discrepancy is more. Whereas this here the discrepancy in quasi is low. That's why it's called low discrepancy sequence. Okay, this is more technical term than calling it as a quasi-random, because that's not a random at all. Okay. You see, what is the advantage of this low discrepancy? If you look theoretically as well as practically, it can converge the calculation faster, whereas the pseudo-random numbers takes longer time to converge. For example, you see, if your value you start with this one for no iteration, and if you do more iterations, more trial, you will get result converge to a point. Okay. So if you do further iterations, will be like this. That means it is converged. Whereas in pseudo-random numbers, it is like this. So it takes long time. Your number of iteration is more. Here this is the axis, your iteration. Okay, iteration or trials. You have to try more. Okay, trials, number of trials you need to do more in the pseudo-random numbers. So which is a faster one? Can you tell me which is faster? Quasi or pseudo?
Less trial.
Huh?
Less trial.
Yes, that's trial. That is quasi the faster one. How it is mathematically we can say look, the error in pseudo random number is inversely proportional to square root of n, whereas here it is inversely proportional to n. For example, if you have iteration is 100, here what is error? It is 1 over square root of 100, that is 1 by 10, that is equal to 0.1. Whereas here if iteration is, so you have 10% error there, but if you have same iterations 1 by 100, not square root of 100. So it is 0.01%. 01. So what is the here error? 1% error. Whereas here in the pseudo random number 10% error. This is 1% error for under iterations. Similarly for higher iteration you can see this you can the error reduce much faster here in quasi random numbers. But there is one disadvantage with quasi random numbers. Here you see D, the term D, if increase the and convergence error take long time. It takes more iteration. What is D? D is the dimension. That is D numbers of random numbers were estimated per iteration. Okay. Per trial, you are getting D number of dimensions, D number of random numbers. Okay, it is at present how many random numbers are getting from this one C++11 library? One random. For instance, you can get one random number. But if you can get two random numbers, three random numbers, that will be helpful, right? For some cases. For example, in this equation, you see equation 1, y equal to f of x comma random plus g of x comma random. Okay, so it needs two random numbers. You can either call one by one, or you can call at the same time. You can get same time. So getting same time from this single engine is faster than calling that engine two times. So this equation is a two-dimensional equation. So it demands a random number and produce two random vectors per event, okay, per trial. Let us see the equation 2. Here how many random numbers are involved? 3. So 3 means what is the dimension? 3 dimension. It's a 3-dimensional vector is needed from the random number generator. So if this dimension increases, then the error will also increase because they are proportional. Right? This term is proportional. Here you see the altern and enzyme both are not doing very well when dimension going up, whereas the Sobel goes bad as bad. It reaches the level of pseudo random numbers at higher dimension. At lower dimension, it is working very well. At higher dimension, it goes to the worst case of pseudo random number. Okay. So if we take efficiency, this is dimension. Okay, dimension D, efficiency. The pseudo random number is like this. Okay, pseudo. Whereas the Sobel number goes almost like this. Okay, that's just at high dimension. This is Sobel. Whereas the altern and that goes above. So we don't need to. You'll just ignore the altern and enzyme because they are not stable at higher dimension. Okay, whereas a Sobel, it's very good at, sorry, this efficiency is like this. You can say error, you can say this is error. Error is lower at low dimension. At higher dimension, it reaches the level of pseudo random number. So we keep the Sobel, ignore the alter and end sign. Okay. So Sobel is the number which we are interested, because that error is very less at low dimension, and at higher dimension it reaches the level of pseudo random numbers, and it uses a primitive polynomial based bitwise arithmetic without carry. That's all. So this uses a bitwise arithmetic, because simple if you do a integer arithmetic, that is a time taking process compared to binary arithmetic. So it uses the binary arithmetic. Even the Mr. Twister also uses the binary arithmetic. So that's why they are doing a lot of complex work, complex mathematics, but they are doing it in binary arithmetic and shift registers, so they can do very fast. That's why they could produce random numbers in a considerable short time. Okay. So what is the thing we are going to taking from this page? The low discrepancy sequence are better in convergence. Sobel number is the best for considering low discrepancy sequence, because that has very less error, that produce very less error at low dimension, and at higher dimension it reaches the pseudo random conversion. Okay. If you want further theory about these numbers, this book is the best one to refer. And another book also there that is also dedicated to this subject.
I had no idea it was so widespread.
Okay, you can have this. You will have this presentation file, so you can have it. You can look into that. And now another thing is this dimensionality we talked about. We saw about equation 1, equation 2. Equation 1 needs 2 random numbers. Equation 2 needs 3 random numbers, like that. Where it is necessary. For example, in games, game coding. This is one book about game coding. They say most games need multiple discrete stream of random numbers, right? Because if you make a 4 birds flying, okay, so each bird needs about 3 random numbers at each event, because 2 wings and direction of movement, okay, so 3 random numbers they may require. So this simulation needs how many random numbers?
4.
Yes, 3 times 4 is 12. 12 random numbers it requires. So its dimension is 12. Then only it can manage the time and make a proper simulation. Okay, so the dimension already have to include it in the C++ random number generator, because at present it is producing only one random number. Similarly, in some of the financial calculation, you need to provide separate random number for each of components. For example, if in a year calculation, give one random number for each working day. So at that time you need the D is minimum greater than 250 random numbers requirement. Okay, the D requirement is become more than 250. Our C program, it supplies only one at a time. If you look at the modern this one Mr. Twister or Sobel in the numerical receipts book, you can have this book. This numerical receipts is a fantastic book for all the numerical work, and it has the full library for random number generation. So in this one you have the multi-dimensional random number generations for this Sobel as well as Leslie Twister, and then that we can use it, and our aim for the C++ 17 is add dimensionality to random number generation, then add Sobel number. Also, you have to see how to decrease the complexity of discard. Then implement the user-friendly methods in random. For example, pick a number in the integer form from given set of integers. Pick a number, so it will be very user-friendly functions. So these are the plan for C++17. Now we have gone up to the fortran to C++17, and there are something more happening beyond this scope, present scope. That is, you saw the random number generated from only earlier from radioactivity, and then it was started with mid-square method by Newman, and then it has come to congruential methods, and then Mr. Twister, Sobel, and there are still people trying to see whether we can get true random numbers from hardware. So that is also people working on it. However, it is not sufficient for our fast simulations. So we have to go for other direction. That is called GPU programming. What is GPU programming? Earlier, the GPU, graphical processing unit, was used only for graphics display. And one of the employee in Bloomberg got an idea that if we do a small calculations with GPU, because each unit of GPU can store a floating number. So if you use a small calculations, how would it be? He tried a calculation, it worked, and he thought, when can we do a concurrency in GPU? He tried, it worked. So that became a popular one, because in each computer has hundreds of GPU, whereas it has the CPU it has 4, 5, 10, whereas in GPU you have hundreds. So if you use them for doing small calculations and then combine them, then you can solve problems in quicker form. NVIDIA thought this is the best opportunity for them, so to make use of this idea. So they expanded from graphics display to high performance computing, and using GPU now lot of supercomputers are made. That saves money, space, time, everything, and that performance is very good. And similarly, Microsoft is Visual Studio is supporting the accelerator mass programming, and OpenMP also come up with GPU programming. It says it is working better than CUDA. CUDA is the division in NVIDIA for this GPU programming. So the OpenMP is now declaring that it is doing better than Microsoft and NVIDIA. So this is the competition is going on now. And one interesting thing is the CUDA, that is the NVIDIA division, has made a library called CURAND. So it is random generator library. It is for the generating high quality randoms. They are well tested, and then so we don't need to make a random number generator there. It's already established. That will produce both Sobel number and Mr. Twister. Both are well established one, and you can see the performance also very good. now in the CPU we can get some million samples per second, but with GPU we can go for giga samples. So here you can see the red is the Sobel. This green is the Mr. Sister. Similarly, here also Sobel Sister. These are the our popular models. So they are getting into a good quality. This is the this one engine. This is the distribution with engine. So they get the normal distribution with engine. So what we say equation pi is this one. So they got it, and so we can get 1 giga samples. Instead of million samples, we can get 1 giga samples. So our speed will increase by 10 times or more. So this is the latest random library, and its performance is very good. And there also we have to make sure we need to do discard, because same random number should not be read by same thread, different threads. So each thread should read different set of random numbers. So that we have to do skip ahead or saving state to avoid overlap. That we have to do. That is the user responsibility, and they have dedicated L file libraries. Okay. Now we have covered the random numbers from the prehistoric period to CUDA library, random library. So I want to ask a question. So far, lot of random generator we saw, but none of them is better than what we have now across our table. We have wonderful random generators. Can you guess where are they? Can you guess? Wonderful random numbers, better than all these random numbers.
Anything physical.
Anything?
Physical.
Physical also not that fast. Okay, not that much one. It is much faster. You don't know. Okay, I'll try. You realize our brain is the source of random numbers. Okay.
But that's physical object.
Physical, correct? That's not real physics, it's biology also. And then it accesses the past and present data, generates random scenarios. It simulates future, be it next minute or next decade. Okay, correct? It already has a plan for today and what is the plan for tomorrow, what the plan for next year. So it's already simulated. This is a sophisticated random generator, very smooth simulator, but it is of bit biased. Okay. Pessimistic brain skewed towards negative random. Optimistic brain skewed towards positive random. Okay. Thank you. Any question or suggestions? You can write it in the comment also. Okay. Thank you, Eunice.
Cool.
Okay. Thank you, everybody. Bye.